Hi, hello students, good evening everyone. Okay, I hope all are doing well. And I believe I am perfectly audible and visible to each and everyone present over here to watch this particular session. Yes, fine. And today we are going to the next part of our same chapter, that is thermodynamics. We will be starting with the laws of thermodynamics very quickly. Hi Priyanshu, good evening. Yes, Anish, I am fine now. No issues. Okay, we will be starting the lecture with the laws of thermodynamics, right? Which is a very important chapter, very important subtopic which is in the thermodynamics. What are the main important laws we have studied? Or you have an idea, right? Laws of thermodynamics. What are the major laws of thermodynamics? Okay, there is a humble request for all of you. My energy is very low today, so I need your complete support or complete response from your side. That will boost up my energy. Okay, what are the major laws of thermodynamics you are familiar with? First law, second law, right? So we will be starting with the zeroth law of thermodynamics. That is zeroth law of thermodynamics. Okay, then we will be moving to the first law of thermodynamics, second law of thermodynamics, and finally move to the third law of thermodynamics. Here in this particular session, we will be focusing on zeroth law as well as first law of thermodynamics. So let us start with the zeroth law of thermodynamics. For example, I will give an example like this. Okay, if I am taking three bodies, right, A, B and C, I can say that if two bodies A and B are thermal equilibrium with the third body C, right? This is in thermal equilibrium with the body C, and again B is also thermal equilibrium with the body C, right? And then what do you mean by thermal equilibrium? I hope everyone has the concept of equilibrium, right? If I am taking the thermal equilibrium, it means the temperature should be same, right? The temperature should be same. Which means there is no any flow of heat between the systems, right? So if I am taking here, if I am taking here two bodies, right, A and C are in thermal equilibrium with each other, which means that if I am taking the temperature of first body as TA, right, as TA, then the temperature of third body as TC. So if I am saying that two bodies A and C are thermal equilibrium with each other, I can say that their temperature are equal, right? TA is equal to TC. Similarly, if I am taking the second body, right, if the second body B is in thermal equilibrium with C, I can say that the temperature of B is equal to temperature of C, right? TB is equal to TC. Yes. Now we can say that what you can see over here, TA is equal to TC and TB is equal to TC, right? Which means that TA is equal to TB, right? TA is equal to TB, right? Any doubt how it is became? TA is equal to TC, TB is equal to TC because they are thermal equilibrium with each other. So here I can say that TA is equal to TB. Little maths, right? So in chemistry words or thermodynamics words, we can say that these two bodies A and B are also in thermal equilibrium with each other. They are also in thermal equilibrium with each other. Right? So this will be the definition of zeroth law of thermodynamics. Whenever two bodies A and B are thermal equilibrium with another third body C, we can say that the first two bodies are also in thermal equilibrium with each other. So we can say that it will predict the condition for temperature, right? Clear? Is the thing clear? Just let me know. If it is clear, just give me the thumbs up. Yes, fine. Now let me move to the important part, that is the first law of thermodynamics. Okay, first law of thermodynamics. I hope you guys have revised through the previous sessions we have discussed in the previous classes, right? We have studied about the internal energy part, work done, heat and everything, right? So here this is the first law of thermodynamics is the part of internal energy. So I can just define this first law of thermodynamics as the energy in a process, right? Energy in a process may be transferred from one form into another, but it is neither created nor destroyed, right? Energy can neither be created nor be destroyed, which means that energy is always conserved. Energy is always conserved, right? So we can just simply say that the definition for first law of thermodynamics is that energy can neither be created nor be destroyed. Otherwise, this same law is also known as law of conservation of energy. Energy is conserved. Clear? Law of conservation of energy. Now, according to the thermodynamics, we will be introducing a term like internal energy, right? This is the complete energy of a system. So, we can say that whenever we are giving any energy to the system, it will be using for transferring heat as well as doing work, right? Let us say Q, then doing work. The energy which is given to the system is used for transferring heat as well as doing work. Let's say it is W. So that in mathematical expression or mathematically we can explain the first law of thermodynamics as delta U is equal to Q plus W, where delta U is the change in internal energy, Q is the heat transfer, right, whether it is absorbed or liberated, then W is the work done. Clear? This will be the mathematical expression of first law of thermodynamics. You will be getting more problems according to this particular expression. Clear? Now, let us move to the advanced version here. If I am taking an isolated system, right? If I am taking an isolated system, which means that there will be no any energy exchange as well as work done, right? Which means Q is equal to 0 here for an isolated system, as well as the W, work is also 0 here. So what will be the expression here? Delta U is equal to Q plus W, 0 plus 0, that is equal to 0, right? Yes, delta U is equal to 0, which means that internal energy is a constant, right? That means change in internal energy is equal to 0 means that internal energy is constant. So we can define first law of thermodynamics as one more term, that is the energy of an isolated system is constant. Energy of an isolated system is constant. Is the thing clear? Now, based on the IUPAC convention, we will be discovering or we will be defining these terms, right? These terms according to their different signs. So, as already I have mentioned in the previous session, whenever we are discussing about the work done for the system, we can say that particular sign is given to the system, right? If the heat is absorbing by the system, we will take it as positive, right? If the heat is absorbed by the system, it will taken as plus Q, that is positive sign, right? Then if the work is done by the system, work is done by the system, right? Work is done by the system, that is the expansion work. We can say that W will be negative, right? W will be negative. So that we can define or remodify the first law of thermodynamics as delta U is equal to plus Q minus W, where minus comes from the work done by the system. Clear? You must have an idea about how we are using the signs here. According to these different equations, you will get the numerical problems. Now, the second condition is that if the heat is absorbed by the system, what will be the sign? Minus or plus? If the heat is absorbed by the system, absorbing, right, it will be positive. So, we can take it as plus Q. Then, work is done on the system. Work is done on the system, that is compressing, right? Work is done on the system means compression work, we can take it as positive, right? It as positive plus W. So again we are remodifying the first law of thermodynamics as delta U is equal to plus Q plus W. Clear? Okay. Now the next one, heat is liberated, right? Heat is liberated or heat is releasing from the system. Releasing by the system, so we will take it as negative heat or minus Q. Then work is done by the system, right? Work is done by the system. Expansion work, W is equal to negative minus W. So remodifying the first law of thermodynamics into delta U is equal to minus Q minus W. Similarly, if the heat is liberated by the system, minus Q, right? Liberated. Work is done on the system, that is plus W. Remodifying delta U is equal to minus Q plus W. Clear? While solving the numerical problems, you must have an idea about that. What will be the sign for the particular system, right? If the work is done by the system, it will be negative. If it is work done on the system, it will be positive, just like that. Clear? Hi Aishu. Good evening. Now let us talk about the process, right? Process which is at a constant volume. Otherwise, we can call this process as isochoric, right? Isochoric. A thermodynamics process which is happening at the constant volume condition. Isochoric, which means change in volume will be 0, right? Change in volume, dV will be 0. So we can say that work done is equal to, work done, we have already discussed about work done is equal to the P dV, right? Minus of pressure given, pressure into the change in volume, delta V or P dV. Here already the change in volume will be 0, so which means that W is equal to 0 for an isochoric process. W is equal to 0 for an isochoric process, which means there is no any mechanical work done in a isochoric process. Yes, Aishu, I am fine. And what about you? Everything going good? Yes. Then we will be discussing about the work done, right? As the consequence of first law of thermodynamics, we will be taking about the next process which is happening at the constant pressure, which we can say that isobaric process, right? The thermodynamic process in which the process happening at the same pressure condition is known as the isobaric process. So, what about the modification of first law here? As we already know, delta U is equal to Q plus W, right? Q plus W, where W will be the pressure into volume work, right? Pressure into volume. So, I will written it as Q, yes, Q minus P dV, where negative stands for the work done by the system, right? Work is done by the system. Then pressure volume work is given by P dV, or we can write it as Q plus W or Q minus P dV. So I am elaborating this delta U as U2 minus U1, right? Because internal energy is a state function, right? Yes, great. Internal energy is a state function, right? So which means that we can find out the value by initial as well as final state, right? Initial as well as final state. So we can written it as U2 minus U1 is equal to QP minus PdV, right? QP stands for the heat exchange or transfer of heat at the constant pressure condition. So it will be U2 minus U1 is equal to QP minus PdV. Then again I am elaborating the dV as P into V2 minus V1 because volume is a state function, right? So we will written it as U2 minus U1 is equal to, yes, U2 minus U1 is equal to QP minus P of V2 minus V1. Open in the bracket here, it will become, yes, open in the bracket here, it will become QP minus P V2 minus PV1, right? QP minus PV2 minus PV1. We already know that PV is clear, right? PV is here. So I am taking here, QP is taking this side, then U2 will go that side, right? Are you getting the point? So QP will go to the left side, then U2 will go that side. It will become U2 plus PV2, right? U2 plus PV2 minus U1 plus PV1. Then I should thanks for the compliments. Then here QP is equal to U2 plus PV2 minus U1 plus PV1, right? In the previous session, I mean in the yesterday's class, we have discussed about the new term, that is the enthalpy. Enthalpy has given as the sum of internal energy and the work, right? Sum of internal energy as the work. So I can call this as U2 plus PV2 means H2, right? H2. This will be H1. H2 minus H1, or I can written it as QP is equal to delta H, right? So enthalpy can again defined as the heat absorbed at the constant pressure condition. Clear? Heat absorbed at the constant pressure condition is also known as the change in enthalpy. This will be the derivation. Clear? Just let me know. You must have an idea about how it is coming. No need to remember complete derivation step. This will be the important part. How we are calculating the numerical problems. That is only. Yes, fine. Now based on the first law of thermodynamics, we have already discussed about the Zeroth law as well as first law of thermodynamics. Based on that concept, there will be some problems, numerical problems to be solved. This is the first question for you. The question is, if a gas absorbs 200 joules of heat, 200 joules of heat and expands by 500 centimeter cube against a constant pressure of 2 into 10 to the power Newton per meter square, then the change in internal energy is, what will be the change in internal energy? Delta U should be calculated, right? What will be the answer? Give me the answers in the comment box. Options are already given here. Recall the things we have studied in the previous sessions about the first law of thermodynamics, then IUPAC convention of work and heat, then apply the expression here. Then how can we approach this question? Just give me the ways where we can start, what will be the starting steps. First you have to written the terms which is given in the question, right? It is given that a gas is absorbed 200 joules, right? It is absorbing 200 joules of heat. So first thing you have to be noted that what will be the sign of particular heat, right? So I can take here, it is absorbing, right? It is absorbing, which means positive. So I will take it as plus 200 joules. Any doubt? Because heat is absorbing here. For the absorption of heat, we are taking Q is equal to positive. So it is 200 joule here, taking Q is equal to 200 joule. Then what about the change in volume here? It is saying like that it will be expands by 500 centimeter cube, which means the change in volume will be 500 centimeter cube. Clear? the change in volume will be 500 centimeter cube. Then already pressure is also given here. I am taking here pressure is equal to 2 into 10 to the power 5 Newton per meter square or Pascal, right? Newton per meter square or Pascal. Then we have to find out the change in internal energy. Then each and every word in this particular question is very important. So this is expanding, right? This is expanding, which means that work done is equal to negative here, right? Work done is equal to negative here, that is equal to minus P delta V. Minus P delta V. Then calculating by using the numericals given here, 2 into 10 to the power 5. Then you must be converted into the SI unit, right? Meter cube. So I will multiplying it with 500 into 10 to the power minus 2 stands for centimeter. Whole cube means 10 to the power minus 2 whole cube. It will become 10 to the power minus 6. So it will be 500 into 10 to the power minus 6. What will be the answer? $100, right? Work will be 100. So we will be applying the first law of thermodynamics here. Delta U is equal to Q plus W, where Q is equal to, it will be negative, right? Because it is expansion work, minus 100. Then Q is equal to 200 here. 200 plus minus 100, that is equal to 100 joule, right? Then in the options, 100 joule is not given here. So you have to convert it into the calorie. One important term you have to be noted that 1 calorie is equal to, 1 calorie is equal to 1 joule is equal to 0.2392 calorie, right? 0.2392 calorie, or simply we can say it as 0.24 calorie. So while converting this 100 joule into calorie, it will become 23.92 calorie, which means option A will be the correct answer. Yes, option 1 will be the correct answer. Clear? Okay, here is the next question. The delta U is equal to that is the change in internal energy is equal to the whether it is adiabatic work, isothermal work, isochoric work or isobaric work. Just apply it on the first law of thermodynamics in the mathematical expression of first law of thermodynamics. Then in order to answer this question, you must have an idea about what does mean by the adiabatic, isothermal, isochoric and isobaric processes. Then what will be the answer? Isochoric. Okay, those who given the answer as isochoric, I didn't get his name, that is like he or she, I don't know. Okay, isochoric, let us take. Then what about others? Adiabatic. Okay, right, let's check what will be the answer. Yes, option 1, adiabatic, right? Adiabatic is the correct answer. So, in order to approach this question, you must have an idea about what are the different types of thermodynamic process. So, then will be the application of first law of thermodynamics, right? Delta U is equal to Q plus W. Then it is given as Q is equal to W, right? You have to identify which is the work, adiabatic, isochoric, isothermal or isobaric, right? So, in the case of adiabatic process, in the case of adiabatic process, right? In the case of adiabatic process, there will not be any heat exchange, right? Which means Q is equal to 0. Q will be 0 for an adiabatic process. Then we can say that the change in internal energy is equal to the simple work done, that is equal to the adiabatic work done, right? Adiabatic work done. So option A will be the correct answer. Clear? Yes, Reyes, you are correct. It is adiabatic work. Then isochoric, right? Isochoric. What do you mean by isochoric process? The process is same volume, right? Which means delta V is equal to 0, right? Delta V is equal to 0. Therefore, pressure volume work is also 0, or W is equal to 0. So we can written it as delta U is equal to Q only, right? Delta U is equal to Q only. Right? Yes, delta V is equal to 0 for an isochoric process. So what will be the expression here? Work will be 0. Isochoric work will be 0. We cannot predict from the internal energy here. So here we are already derived one more term here, which means that the heat exchange happening in the constant volume condition should be equal to the change in internal energy. Change in internal energy. Clear? Here the option A will be the correct answer, option 1. Right. Then here is the next question about the adiabatic expansion of an ideal gas. During the adiabatic expansion of an ideal gas, 100 joule work is done. 100 joule work is done. What will be the internal energy? Delta E means internal energy. You can use it as delta U or delta U. What will be the answer? Option B, right? We have already seen that in the case of an adiabatic process, the work done should be equal to the change in internal energy. So it is given that work done is here 100 joule. So delta E is equal to adiabatic work, that is equal to W adiabatic, that is equal to 100 joule, right? Clear? Then you must be aware that whether the work is done by the system or work is done on the system. And it is, okay, there is one more correction, that is, it is the expansion of an ideal gas, right? Expansion of an ideal gas. So, option 4 will be the correct answer, right? Option 4 will be the correct answer. Which means, in the case of expansion work, W will be taken as negative. Minus 100 joule will be the correct answer. Clear? As it is different from the physics concept, right? You must have an idea about in the chemistry also. Chemistry is, if it is the work done by the system, in chemistry it is taken as negative. If it is work done on the system, it will be taken as positive, right? It is little bit confusing, right? By practice only you will get the exact idea. Ready? Now here is the next question. The 90 joules of work is done on the surroundings when a system absorbs 180 joules of heat. what will be the change in internal energy during this process? Okay, values of heat and work is given here. You must think about what will be the sign, then apply it on the first law of thermodynamics. Okay, what will be the answer? Just give me the answer. Option is given here, right? 1, 2, 3 or 4. Option 1, right? Option 1 will be the correct answer. Here, work done is right 90 joules. Work is done on the surroundings. This is very important. Whenever we see done on the no, we will be taking it as positive. But it is wrong. Work is done on the surroundings by the system. We will be taken about system only. So, work is done on the surroundings by the system. It will be negative, right? Minus 90 joule. Then, what about the heat here? Positive or negative? System is absorbing heat, right? So it will become positive, plus 180 joule. Plus 180 joule. Apply first law of thermodynamics, that is delta U is equal to Q plus W, general expression. Then Q is given here 180 plus minus 90, right? 180 minus 90, that is equal to 90 joule. Which means option A will be the correct answer. Clear? Yes, heat positive as the system absorbs. So, whenever we are solving about the thermodynamic problem, the each and every word present in the question will be very important, right? There will be some confusions, right? The question itself will be confusing, so wrong answer may get. Clear? Then here is the next question. A system absorbs X joule of heat and does Y joule work, right? A system absorbing X joule of heat and does Y joule of work. If its delta E is positive, what will be the condition? Whether Y greater than X, X greater than Y, Y is equal to 2X or X is equal to Y. Is the question clear to you? Is the question clear to you? Yes, X greater than Y, right? Okay, what about others? Okay, can you please mention your name in the comment box? Just let me know who is the one giving the answers. Okay, system is absorbing heat, right? Absorbing heat means positive. So, plus X, right? Then, it does Y joule work, which means work is done by the system, right? Work is done by the system. It does work means work is done by system. So, it will be taken as minus Y. Value is given here, it is Y joule. So, sign will be negative. Apply first law of thermodynamics, that is equal to Q plus W. I am directly written it as X minus Y, right? X minus Y. You can again written this delta U as delta E also, it is right. So, condition is that the change in internal energy will be positive, right? Change in internal energy will be positive. So, we must have an idea that when this value become positive, whether it is X greater than Y or Y greater than X, right? So, we can say that X greater than Y will give the value of positive here, which means option B will be the correct answer. Clear? Fine. Now here is the next problem. This is based on the work calculation in the isothermal process. We have already discussed in the previous session, I mean the yesterday's class, about to calculate the work done during an isothermal process. Here the question is, a piston filled with 0.04 mole of an ideal gas expands reversibly from 50 milliliter to 375 milliliter at a constant temperature of 37 degrees centigrade. As it does so, it absorbs 208 joule of heat. What will be the value of Q and W, which means heat and work of this particular process will be? Okay, what will be the answer? Okay, let us check whether it is the option A or not. Okay. Yes, you are correct. Option A is the correct answer. So, how we can approach this question? How we can calculate the work done during this particular process? This is the isothermal reversible process, right? Isothermal reversible process. There is a simple formula to calculate the work done during an isothermal process, that is equal to minus of 2.303 N. N stands for number of moles. R is the universal gas constant. T is the temperature. Log V2 is the final volume divided by V1. That is the initial volume, right? V2 by V1. So, all the values are given here. You have to put the inputs here and then you will get the answer. Right. Number of moles is given here 0.04, right? 0.04. Then already it is given that the value of gas constant is equal to 8.314. So putting here 8.314 into log volume is changing from 50 ml to 375 milliliter, right? Which means that final volume is 375 and the initial volume is 50. So I am taking here 375 by 50. Okay, you may do the calculations. Final answer will be getting about minus 207.7 joules. So, it is approximately equal to minus 208 joule. Right? This will be the work done. Then, what about the heat here? Heat is absorbing, right? It is absorbing heat of 208 joule. It is absorbing the heat of Q08 joule. 208 joule rule. So that is equal to plus 208 joule, right? Okay. This will be the exact way to calculate the isothermal work done. Then there is one more short trick or simple trick. We can say that this is the isothermal process, right? Isothermal process. So delta U is equal to 0. As delta T is 0. So, what will be the value here? Q is equal to minus W, right? Applying the first law of thermodynamics, Q is equal to minus W. Q is already 208 joule. Then what will be the work? Negative sign, right? So, plus 208 joule and minus 208 joule is the correct answer. Clear? Yes, you are correct. There is no calculation required. U is equal to 0, then Q is equal to minus W. Clear? Okay. So far we have discussed about the Zeroth law of thermodynamics and first law of thermodynamics. Now I will be moving to the next part, or a part of thermochemistry, that is about the thermochemical equation, right? Thermochemical equation. So we can define a chemical equation as thermochemical equation whenever this contains the value of enthalpy change, right? So we can define that a balanced chemical equation along with the values of enthalpy change, that is delta H value, is called as a thermochemical equation, right? Thermochemical equation. Then in the particular equation, the physical state of each of the substance, right? Whether it is reactant or product, the physical state should be mentioned. It should be specified. For example, if I am taking this particular reaction, right? C2H5OH, which is in the physical state of liquid. So I am mentioning here small letter L. Then oxygen, it is in gas state. Carbon dioxide, water in liquid. Then the value of enthalpy, that is delta RH0, that is the standard enthalpy of reaction, that is equal to minus 1367 kilojoule per mole. The conditions are, it should be balanced, right? This equation should be balanced. The physical state of each of the terms should be mentioned here, whether it is allotropic form also. Then delta H value is also mentioned here. So I can say that this particular equation is an example of thermochemical equation. Clear? Now, you must have an idea about that. What are the conditions to satisfy a thermochemical equation? It should be balanced, right? It should be balanced. Delta H of the reaction should be provided. Then, physical state of reactants and products should be mentioned. Whether it is there in the allotropic form. For example, if I am taking carbon, whether it is graphite or diamond, you should be mentioned that carbon in bracket, it should be graphite, right? It should be graphite. For example, is given here. Carbon, graphite plus O2 gas gives CO2 gas along with the delta H value, right? This will be an example of a thermochemical equation. Okay, based on this idea, you may have the questions like find out the equations which is found to be thermochemical. So the conditions should be satisfied are balanced one, delta H value should be mentioned, and the physical state is also mentioned along with their allotropic form. Clear? Okay, now we will be explaining the one of the term which is given in the thermochemical equation, that is the enthalpy change of reaction, right? Enthalpy change of reaction, otherwise it is also known as heat of reaction, right? Heat of reaction. Whenever we are considering any of the chemical reaction, it is happening, the reactants is completely changed into products, right? Reactants is completely changed into product. So we can say that the enthalpy change accompanying a reaction is known as the reaction enthalpy. Okay, Shyam, what is your doubt? Okay, I will be continuing from here. Heat of reaction, right? Heat of reaction. For example, if I am taking if I am taking this particular reaction, that is AA plus BB gives CC plus DD, right? So we can written the heat of reaction or the reaction enthalpy as delta H is equal to right? This will be the exact explanation of the delta H enthalpy change for the reaction, or we can take it as this will be the multiplying with the stoichiometric coefficient. Okay, wait, I will just complete this and then I will come to your doubt. Okay, here we can write the enthalpy of reaction, right? Enthalpy of reaction is equal to the, this will be the enthalpy of formation of the product C into their stoichiometric coefficient, right? Into their stoichiometric coefficient. So we can write it as delta H is equal to sigma AI into H of product minus sigma BI into H of reactants, where AI and BI are the stoichiometric coefficients. Clear? Based on this particular formula, you may get the more numerical problems to find out a reaction will be given to find out the complete reaction enthalpy or the enthalpy change during the particular reaction. Then each reaction having the enthalpy value should be given in the particular question. You just multiply with the stoichiometric coefficients of product as well as reactants. Clear? Then okay, this is the important term we have already discussed in the previous session, that is delta H is equal to delta U plus delta Ng RT. Here the actual term was pressure volume, right? So we are applying the ideal gas equation here, PV is equal to nRT, then you will get P delta V is equal to delta Ng RT, where delta Ng is the change in number of moles of gaseous products and gaseous reactants. Clear? Again, this is also very important to solve the numerical problems. Clear? Okay, what is your question? Okay, I didn't get your question. Shyam, can you please type again? Water twice, right? Okay, you got to your answer, right? Actually, I didn't get your question. Okay, I hope your question was clear and your answer was also clear. Okay, Gibbs free energy, right? Okay, we will be discussing detail about the Gibbs free energy and the second law of thermodynamics. Detail in the next class. So, You will get the answer for that. Clear? Okay, that's all about from my side for today. Again, reminder about the AATS. You will get the special discount of 2,999 using this special code, that is U250 off. So don't miss it, just enroll fast. Okay, so far we discussed about the thermodynamic process, right? Starting from the basis of the thermodynamics, we have studied about the thermodynamic process, including work and heat. Then we will be starting about the laws of thermodynamics. First, we discussed about the Zeroth law of thermodynamics, which will describe about the terms in thermal equilibrium, right? Then we will be moving to the first law of thermodynamics, which will explain the relation between internal energy as well as heat and work done. So that's all about from my side for today. I hope I will be coming back with the next class along with the second law of thermodynamics, which will explain about the entropy. So till then, bye bye all of you. Take care. Thank you so much.
हेलो, मेरा भी यहाँ से साउंड जाना चाहिए, नहीं जा रहा है, यहाँ पे दिख रहा है।